the high temperature stage. So your limit is 350. But say you stayed at 350 for a long time, eventually your arm sitting over there may get up to 350, right? And then you'd have to cool it back down and then go back up, and that window would be the window time that you have to use it. Okay. There's an option stage that you can put in that will go to 675 that people use on.
But we don't have it.
You don't need it. Yeah. So, again. All the arms are the same as far as how they move, you know. We have X, so going in and out, Y, and then Z. And you'll see there's an arrow here on Z telling you which way is up, okay? And it's a good habit to look at that before you move this, right? Because sometimes these are way out of focus maybe, and it's hard to tell if you're going up or down, so you don't crash into something. The DC probes are pretty robust, so they're gonna bend some, but you know, you're just looking for a touch contact. But like with RF or other types of probing, you could damage the probe because like an RF probe is pitched, right? So if you bend one of the little prongs, yeah, it's no good. You have to, hopefully you're gonna get it repaired, but a lot of times those ones can't be repaired. They have to go out. Again, we're using so you can use nitrogen or argon for purge gas. It's not 100% necessary to use it, but it makes the system run much more efficiently when you keep it clean. Okay, so without it, then you're always pumping water, and yeah, it'll just be dirty, and you want to get the cryo pumping that you want, and it'll still work, but it just won't be as nice. This, you keep it clean, it'll pump down. By the time this comes up to speed, you'll be ready to start your compressor. Your cryo pumping will be really good. You'll get better vacuum. So it's good to use the purge and try to keep the system clean. Yeah.
So the nitrogen current factory, it has to be always open, this valve?
Only when you have this cover on.
Cover off.
Yeah, you don't want to turn it on now because we're under vacuum, right?
Okay.
So only when you're going to exchange your sample are you going to use a purge gas. So as long as the cover's off, you should have this running.
So is it like after taking off the cover, we should turn it on, or before taking off?
We're gonna stop the vacuum, isolate the vacuum from the system with this isolation valve.
Okay.
Now that that's isolated and off, then we can purge.
And then we will remove it.
Yeah, once it's purged, then this cover's gonna rattle a little bit, and then we're gonna take it off, and we're gonna leave this on until we put the cover back in.
Okay.
Yeah. The gas is heavy, so it will fill up the chamber and roll over, and kind of keep the atmosphere out again. And then this way, your pump isn't also pumping atmosphere all the time. It'll be pumping nitrogen, right? So we'll have nitrogen in there. We put the covers back on. We open that isolation valve, because when we stop the pump and close this, we have to open the vent valve on the pump and vent this part. So this is going to be under atmosphere, right? So if we put our covers on, open this up, now the nitrogen is going to purge out there, and then your pump's not pumping on atmosphere. Then we close that, close this, turn that on, and then it will start pumping. And it's just to prevent, your pump will last longer as well if it doesn't have, it's hard pumping water. So it just makes the pump last.
So to make sure that before we open the lift, we blow the valve and turn the gas on, right?
Yeah,
and then we put the sample in, we close the lift, and open the valve again, and pump.
Yeah.
We're gonna write the manual.
We're gonna do all that.
Yeah. We're gonna write some sort of to the manual and put it right here.
So you also the light supply. So the camera has automatic gain control, so we just need enough light that the gain takes over. That way you're not overdriving this light, and also, you know, you're putting heat back into your system with the light as well, right? Some people, they will find something to cover this with, because even these lights can cause heat and stuff, right? You have two different fiber bundles, so you have coaxial light and ring light, and just depending on your sample reflectivity, how it's going to look, right? And it just gives you an option. Before, you had to only have one, and you had to pick when you ordered. Now we do both, so again, you'll put a sample in there and say it looks really gray, like, then you'll just change the light source to have a better image so that you can see. And we'll maybe be able to see that later when we put one of your samples in there, when we go to do it back. So this is, if we were to just cut the system in half, it's kind of how the cold head and the refrigeration system are connected, okay? And right here at where the cold head is, so here's the second CCR, and then the first, and then this is the first stage, okay? And right here is where we have those braids, okay, at this connection. So there's two copper rings on the first and second stage of the CCR, one on the radiation shield and one on the sample, and then copper braids connect the two. And that's how we bring this coldness up here, and also the braids help keep the vibration of the cold head from getting to the sample. So here, it's just showing you like where the sensor and the heaters are located. So what it is, it's the sample stage sensor. It's a silicon diode with a 100-watt heater. And so this has two channels for the heater. One's a 50-watt and one's a 100-watt. And just depending on the configuration of where they're going to put that. And here you see like the second stage. Also, this system is like more the entry-level one, so it only has one controller. So like right now, we still could look at the other CCR, so like, and also the heaters for those. So like right now, we're not using any of this because we don't have enough connectors, right? If you had another controller, then you could look at the other CCR, and you could do the heaters, and it would just heat up even faster than it does right now.
Where is the sensor for the radiation shield?
Yeah, it's so inside there, you know, like you see the sample state, right? Right there where we're looking at.
Yes.
So the sensor is mounted on the back side of that. Okay? And here's the radiation shields right here. So here's the tin can, right? This is the base. And underneath there is the sensor. So the sensor's on this side, the heater's on this side. And the same with the sensor here and the heater's over here. And it's just going to heat just this part right here. The radiation shield's going to heat the radiation. And also it'll heat the CCRs because they're thermally connected. Okay. So that's how we're going to warm the system back up quickly so you can exchange your sample. So the compressor just has, you know, our supply and return gas, and we have cooling water. The cooling water has to be on if the compressor's on. Say we're gonna stop cooling and we want to get to our sample, then we will just turn this off. Maybe leave the water run for 5 minutes, maybe. Or few minutes anyway, because this is still going to be hot, right? Just to give a little cool, and then you can turn the water off after that as well. It has a breaker switch, and then just on and off. So like the breaker switch turns the power on to the compressor, and then you turn on off the switch.
So if you turn it off, you just push one button or both?
Just one, just the green one. Yeah, this just supplies power to the
Oh, all right.
controller. So it does, yeah.
So
You
just-
have one control line, this goes back to the motor,
Okay.
so the control for the motor. And then you have your return gas pressure, and you see the little needle is, like this, right? So on the system, there's a high and low limit for the gas pressure, right? So you fill it up, it came to all charged, right? And you see that little needle pumping like this, right? And what'll happen over time is that you might lose a little gas, right? Because like if you disconnect it to move it, we'll lose a little. There's an absorber in here and stuff to keep the gas clean, so it might over time absorb some of the gas. So what might happen is that the little needle will bounce onto the low limit and it will shut off. So if the gas goes too low, it'll shut off. And in the manual for the compressor, if you follow the troubleshooting, it'll tell you just turn it back on, right? So you turn it on, and it'll only stay on for maybe 30 seconds, right? And then you'll look down your troubleshooting chart, and you'll say, check gas return. And it's just that it needs to be charged a little bit, right? So there's a valve in here. So this valve all comes, and this you're gonna take off the supply line one there, and you're gonna replace this. This is already charged with gas already. Okay. So you're going to take a helium gas tank, like one of those, helium, and a gas line from it. You'll purge the gas, and then you'll put it into here. And then you'll open this up, and then you will set the pressure with the regulator on the tank. Okay? And so you'll just look at that little needle. I don't know, it's 160. It says in the manual what to set it to. And so you'll set that gas pressure to that. Close this, take this off, and then you're back to running again. So, normally, maybe in 2 or 3 years.
Well,
Yeah, if everything works fine and there's no leaks.
It's almost 20 years. And it always
Yeah,
stays,
it's
it's fine, yeah.
like I think in 14 years maybe I had 3 that had to be recharged. And they moved, like one of them they moved it a couple of times.
Yeah,
So it's not something that you got to do all the time. It's going to be rare. Maybe if something happens inside there, like a leak, could do. Might have to use it. If you get a leak, then you have to fix that. So you're just going to charge it back up. If you charge it too much, then it'll hit the high limit, and it'll do the same thing, right? And then you'll release some of the gas to get you to the right point. So if you accidentally recharge it too much. A lot of customers will, since we're installing right now, they'll take a little marker and they'll make a mark where it is right now, stuff like that, just so they know where it is now and if it changed, right? Yeah. So the arms, and so this part of the arm out here with the XYZ is called the MMS. Okay, and they're all the same, and you can interchange the arm position, because some people maybe they have RF or something else, or, you can configure these any way you want. There's 4 screws that hold the base, the 4 on the bellows. And they're like keyed, and then it'll just slide off. And so you can move them around. Or some people, they'll buy this whole part, and then they'll buy different arms that go in it, and then they'll take it out and put a different arm on the inside. Because this part's more expensive. Yeah. You see that the arm is made out of copper, and then there's this green piece right here, that's ceramic G10, and then another piece of copper, and this is where the probe holder is going to go in. These thermal links right here are connected to this part of the arm, and they're connected to the radiation shield. So right now the radiation shield is at 38, so this part of the arm right now is at 38K. There's another piece of G10 here to isolate this, because this is all at room temperature, right? We want to isolate that away from the arm. So now this part's tied to the radiation shield. And then, and also, this is where that sensor is embedded. Is it right out here at the tip? So the sensor is embedded. This one arm right here. That sensor is embedded out here at the end of the arm. Okay. So this is the holder, the probe holder. Right, this part right here, here's the probe. And then this is where this pin is going to go into the end of the arm, so that sensor is right here, right? And then this is thermally anchored to the sample stage. So now this right here is technically like 7 Kelvin, okay? And then you just have just the probe and just the cryogenic wire. So one little bare wire goes there, so that this way the probe is within a few Kelvin of your set point. So whatever you set your set point to, your probe is going to be a few Kelvin off of that. Yeah.
So you mentioned that this is the temperature of the arm temperature, right?
No, this is the temperature of that little sensor right here. So 8 Kelvin, right? That sensor is right here.
And how about the radiation shield? Which one is the temperature equal to the radiation shield? You mentioned 38. It's next to the.
Yeah, this part of the arm is connected to the radiation shield.
Okay, so that is the temperature of the radiation shield. It has the same temperature as the
It's
radiation.
connected to it, so pretty close. And it's again just to help isolate the probe. You know, so you know the whole key is that you don't want the probe at room temperature. You want it as close to your set point as possible. And to do that, we're going to thermally isolate the probe tip from all of it. And we're doing that by room temperature, radiation shield temperature, the sample stage temperature, and then the probe is kind of free floating, right, with just a little wire. Yeah. So that's the key, and that's one of the selling points of Lakeshore is that the probe, like Genesis, they don't thermally isolate the probe like we do. So their probe is somewhere out there. Which might change now that we bought Janus. So Janus and Lakeshore are going to use each other's designs to try to improve these things. Because they do some really neat things too, Janus to keep cold and stuff. Okay, so the probe holder and the probe, so the body of the probe is ceramic. So again, I'm trying to isolate it from the rest of the system. If you were going to use RF, so this is like what an RF body looks like. So they build this for us. So you could take one of these arms and put a semi-rigid cable into it and an RF head and do RF. It's pretty simple. Pull the arm off, take one arm, put the other one on. A lot of people do that. It's cheaper to buy less. Again, this is just like the ring light and the coaxial light. So like here, looking at a PC, the ring light will look like this and coaxial. And it just gives you an opportunity to switch the light so that you can see your devices. Right now, we just have the grounded stage in there. So electrically, this is what it looks like right now. And we just have just the grounded stage. So this stage part, the sample stage, there's many different kinds that you can, like the magnetic one. So that's one of the options that, so you take this one out and you put that one in. We'll do that later when we open it up, but it's just 4 screws. The biggest thing is don't drop the screws. Other than that, it's pretty easy, straightforward. Just 4 screws come out and put on another stage. Different stages that you can get, like the Triaxial Stage. You know, a lot of people use that. You don't have, you have part of the wiring in there. So they wire the inside for the cable. So the little cable is in there that plugs into here. And then this cap that's on the back right here, that cable is going to go to here. And then you would buy like one of these or whatever to hook up to there. And then you would be able to bias your stage. Right now we just have that cable off to the side since we're not using it. So this is just the setup for the like the power and everything to hook up the system, what you need for facility stuff. And then this was just this is all unpacking it. So if you were to move it, you would go to here and follow some of these steps backwards. So mostly, if you move it, is that you want to make sure that you put in these red spacers, okay? Those red spacers go right here on the 4 corners, and they hold the cold head and the cable together. So if you try to move this without these, you'll rip the bellows apart. So the bellows is the only thing that's connecting the two together right now. And I have to go to Boston. Boston, they have the same system, and they try to pick it up without putting those in, and that thing is so it's all bent up. So to get to that, the whole thing has to be tore apart. It takes me like 2 to 3 days, because it's a major, to get that out, everything has to come out to get to it. So it's not an easy thing to do.
Okay, don't do it then.
Yeah, always, again, whenever you have any questions in doubt, just call service. You know, we'll help you out or whatever. But just remember that if you're gonna move it, those have to be it. And then, other than that, it's just unplugging a few things. You can just slide this right off, take these off, they can stay over here, and the system is pretty much back to being able to move. Okay, so this is the configuration of the controllers. So remember, we're using the controllers in closed loop. So we're using the sensor and the heaters as a feedback to control the system. And then also, those are tied into the limits and everything. So if you exceed anything, it'll shut down automatically. Okay? And because you're a super user, again, anytime you hit enter, it saves whatever you did. It's not going to ask you if it's okay or, sure you want to change this or that. Mostly we deal with the channel A, right? All the other channels are just reference to tell us things are cold and they're working, right? But the A channel is where we're going to do all of our control and setup and PID values and all that, right? So you notice that I hit A and it stayed in that display for, I don't know, 10, 15 seconds and then it turned back, right? and that gets annoying because we just want to know what's happening in A. So if I hold the A button and it beeps at me, now it'll stay in this display until I change it. To change it back, you go to display setup, which is 1, enter, and then 4 loops, enter, escape, and now I'm back to the 4 loop display, and I get to see a little bit of everything. So in this display, I get a little bit of information, but not all of it, right? Like here, I can see what my set point is, and I can see a whole number as far as the percentage of the heater is on. Okay. So again, if I hold the button, now it won't go back and forth. So you see we have p-values of 125 in there. Let's go back to this. So if you accidentally change something, you can just come back to these charts here, and it'll tell you the setup of all of the channels. So A, B, C, D. So if I go into sample stage, you'll see now there's some. This is what I'm filling out, right? You see here it says curve 21. So curve 21, okay? You see in here, these are silicon diodes, so it has a curve value of DT670. So if I go back and if I look at the radiation shield, you'll see it says a diode and it says it's using curve DT670. That's a generic curve, right? That's already in the library. Outputs. So if I go to the output settings, so there's 2 outputs on this, but it can control 4. So like depending on your what you got, this might have another controller and an amplifier to run more heaters and stuff, right? And so we're only using output 1 and 2 here. And it says here output 1 is the sample state. And so that's this chart right here. So if you move something in there, then you go to this one, and then you would enter this stuff here. And you'll see here that this is like where you would do set point ramping if you want to do ramping with your temperatures. Let's see. Output. So here's in the input side, it gives it a limit of 370. So your system, the high temp is 350. They padded some, so if you go to 3, you're going to overshoot. Like say if you're going to 350, you're going to overshoot a few Kelvin or something, right? So they padded some a little bit. But typically, so if you go over 370 though, this will shut down automatically. So it has safety built into it that if you try to exceed something, it's going to shut down. So when it shut down, it would come back here and it would tell you it shut the controller off because one of the channels exceeded its limits. And then you would have to look and see, what happened? What did I do? Okay, so that's where you're going to reconfigure it. Okay, so this is the basic operations. This is where you're going to be running the system most time. You see here's the limits that you can go to. Sample stage is 350. We talked about the arm is 350. You should never have to worry about the arm thing. Again, that's normally if somebody's using that high temperature stage, then that becomes a factor. And there's things that you can do. You can so remember we mounted the thermal links of the holder to the stage. If we're going to 670, we could move those over to the radiation shield, or we could leave them open, and it would give the arm longer to go before it heated up. Things like that. So here's your limits of what you're going to have, and then we're just going to. This kind of explains like the area that you can probe it. And as I explained to him yesterday, it really depends on what arms you're going to use, right? Because one arm can reach all of them. two arms like this can reach all. But when you start getting the arms adjacent to each other, then they start coming like this, and then that might prevent you from two arms next to each other getting close together. Okay. So you have to decide, and it also depends on your sample, the size of it, right? So you're going to put your sample here, and then you're going to see if all of your arms can meet your criteria of where you want to land. And then you may have to move your sample around so that all of those arms can get to where you want to go to, right? That'll be something that you'll have to learn and figure out, right? Is where am I going to put my sample there that all the arms I want to use can reach it? Because it can be on the outside of that. Yeah. We talk about X, Y, Z, the stages. And we'll do more of this. This is like when it's out and how to, like here they're plugging in that little cable in there to the Triaxial Stage. But we'll do that when we open it up. Okay, this is all for compressor. So this chart, this little table tells us from base temperature to 20K, 20 to 100, 100 to 250, and 3. And it's telling you that we'll need medium heat. So the heater has low, medium, and high range. Okay. And here they're saying like from base to 20, we're going to need medium heat, right? And then the PID values. So you see that the PID values are all the same across the board. Because remember, this manual was written for 30 minutes, right? So they generically, these will work in 30 minutes, right? But if you tune these a little bit, figure out what works really good, it'll do it like 10. Okay. So I think I have this. Okay, so if we put in and again, remember, whatever I'm going to change in the menu, it's going to highlight it. So, yeah, you kind of look before that, before you start pushing buttons. Again, because it's repetition, and after you've done this 50 times, you get really fast at it. You go, oh yeah, dude. Right? And if you happen to... so if I go into A and then but I didn't push it hard enough, if I hit a button, it goes into. If I hit another button, it'll go into menus, and then I hit enter at the end, and I change a whole bunch of stuff. Again, the you should notice right away, because when you hit enter and it comes back to here, this will say something different than what you anticipated, that you did the last 49 times. So we'll put in a step point, and we'll use it. And just to show you, so we'll use low first. Just we don't believe the book.
So how did you do low?
So I hit a set point. I said 8K, and then I hit heater range, and I just arrowed to low temperature. So now on our screen here. And we see that low is not enough power to get it going, right? So, we're up to 30. It's going to keep ramping. We'll let it go. we'll see it. So far, it hasn't moved the
And
temperature.
what is that temperature, 25?
No, 8. We're trying to go to 8 Kelvin.
Oh, just 8.
We were at
Okay.
7, about
Yeah,
7.
that's correct,
So
yeah.
1 Kelvin. But see, it's not our cooling. So the compressor is on 100%
Yeah,
all the time. Yeah,
Mhm.
we can't adjust that part. But yeah, so we're at 50% almost, and it hasn't. So we'll move this heater range to. So then the next is to look at how do these PID.
But when it's overshoot,
It may, yeah. Yeah, you're gonna, so there's,
it go much faster.
yeah. So there's 2 things to going to a set point. Some people, they don't want their sample to go over the set point. So they'll set a p-value so that it just comes to the set point, right? If you want to get to the set point, you don't care that it goes over a little bit, but you want to have really fast stability, then we'll move it so maybe it goes a Kelvin over the set point, but then it will only move maybe 2 iterations of the set point, and then it'll be flat. Where the other one will take a little longer maybe to get that.
This is A, B, C, D here in the 4 channel we can set up.
What?
A, B, C, D.
Yeah, B is the radiation shield, C is the arm, and D is the CCR. So, does that answer?
Yeah.
Yeah, so these are all, they're already connected.
But we always just using.
Now, that's all for reference and to heat up fast, to change up. The sample stage A is the only thing we use during the time that you're going to use the system for
We want to change set up PID, right?
Yeah, in here we can change the PID values and the heater power rate, low, medium, and high.
So when you want to change that, for example, if I want to change that,
I would just push P and see how it highlights it, and now I can put a number.
put a number and then put set point or not, you need to put set point. Okay, so
Well, no, you push enter. Enter saves everything. So,
But it's not really necessary, right? Because usually it's probably, you don't really need to change it, right?
it was right at the moment. No, I guess it's doing its thing.
Yeah.
Remember, we're only going to Kelvin, so that's not very much. So you'll see, like we'll go to, say we'll go to, I think the book's at 20. So we'll go to, see the book's, this chart goes from base to 20. So we'll go to 20K, and then we'll go to 100, and then we'll go to 2, and then you'll see the steps. And you'll see the reaction, because this is so small of a step that you see the heater is just changing a little bit, right? If I put in a set point of 20, that'll go to 100% until it hits the set point. Yeah, so it just depends on where you're going and how far you're going. So Kelvin is very small move.
Can you set the ramping rate? The ramping rate for the temperature for
Ramp rate.
for
Yeah,
example,
you, yeah.
23 per minute or
Yeah,
10
you
per
can
minute.
set a ramp rate. Yeah.
So how can we do that?
Well, first we get to listen
Yeah,
finish.
it-
We don't want to go in
it's more
between.
intense stuff, yeah.
But if you wanted to ramp like say 0.1 Kelvin per second or
Yeah.
minute or whatever, then in the input under the sample is the ramping. You turn ramping on, and it will ask you what do you want
Okay.
your ramp rate to be, and then it would do that. Yeah.
And if somebody accidentally changed something, is there any reset button just to go back to?
No.
No, there's no reset button.
No,
It's
no.
good,
Yeah,
you
only
figure
with
out
a,
what
so
you
they
want.
do all of that with a computer.
Yeah.
Yeah, so with a computer, you wouldn't do this, then you would do it on the computer and you would have on the lab view all of the control of who can get in and who can do what, yeah. But for here, it's just manual hitting the buttons, yeah.
So yes, very good.
So now it would be just the stability of this, right? And you might have to tune these a little bit more, because like you see how this is jumping a lot, right? So you're not going to get 50 millikelvin of stability jumping from 26K to 30K.
I don't think we need 50
So you-
Kelvin. Yeah, that's not important for us. I mean,
Oh, okay.
plus minus 1 Kelvin is good enough.
Oh yeah, okay. So, well, also the closer these numbers are to nominal, the faster everything will work too. Like so it does take a good that you try to find numbers that like I use 75 and 35. Okay, and I'll put a set point on a 20 and well, so between, yeah, looks like we use this. Okay, so you see it went to 100% because it knew from the 8K to the 20K is too big of a step to just like count up. So it automatically went to 100%. You see our response on the graph, right?
So again, what is P?
P is the proportional.
Proportional.
I
So-
integrator and D the derivative. I don't know Lakeshore. It's always zero.
Not important, yeah.
Yeah.
So if P is greater, so what happens?
So the higher the P value, the sharper the slope to the set point. But then you're gonna probably overshoot a lot, right? If you be real aggressive at it, right?
And
I is the how many times it samples the air over the iteration of the set point. So if you sample too fast, you'll get a correction and this will turn into kind of like a sawtooth, your signal. Because it's trying to change too fast, it's sampling too fast. So then you have to lower your I value.
What are reasonable values just to keep them?
What's the what?
What are reasonable values for P now just to keep them for most of the iteration? What do you recommend?
Well, again, you can do this and it will work. It'll take at least 30 minutes or less, somewhat less. Or you can take a little time and tune it like this. Like, so you see their response, so like we...
That's very quick.
So we only went over a half a Kelvin.
That's perfect,
So
yeah.
that P value was pretty darn good.
Okay, so we'll
Yeah.
keep it like
Now we look at the I value. The sampling is how fast is it. So now I look at this part. Okay, so see now we're coming back to the we're coming back to the 20K, and now so it could have went past it and then like this, right? It halves the air every time it hits the set point is the formula, right? So the closer you have this to your halving,
Yeah,
right,
okay.
the faster that it will settle.
But
Yeah.
wait a second, so we'll keep
But
it
like right now, so we did, yeah. So these numbers are the ones that I usually use out of from the book.
Paul, I have a question.
Yeah.
So these numbers of P and I that you have set for 20 Kelvin, can we use the same numbers for higher temperature as
Sure,
well?
it's fun.
We're
Yeah,
gonna keep it the
because
same number
so
for
you
every
see that's what they did
temperature.
here. They use 125 for the whole thing. Yeah, and you'll get some response. We don't know. But this, like 75-35, looks like it works even better.
Yeah.
One, look at the stability of it. I mean,
Yeah,
we're already at 100 millikelvin.
Yeah, perfect.
And it's only went across like 1-2 times. So if we look at this is happened in 3 minutes so far.
Yeah, very good.
Yeah. So the better you have these, everything just works just much better. So we'll just continue with 75-35. They work really good. We're at 35-20 millikelvin right now.
So when we go from higher to lower, also it will take the same time.
No, not necessarily, because then if you shut the heater off, it's the cooling power, how fast
always
it's gonna be.
different.
You'll have to figure that one out, kind of like as you use it.
I see.
You could like go up to 200 and then let it drop back down and see how long it takes and figure it out.
Because
that
it took
way.
overnight to come.
Oh no, it wouldn't take that long.
Oh, okay.
No, just. Okay, so now we'll set it to, somebody can set it to 100. And we'll leave the P values the same, and we're gonna move to high temperature. So put in a set point of 100 and turn it to high temperature.
You want me to do it?
I want you to do it. I know how to do it. So we're already on a, yep,
100.
100. Enter heater range. Yep, arrow. And you see that it knew from 20 to 100 is a huge jump. So it just turned the heater on 100%. And then it's going to use the P value once it gets there. So now you
It's
see our
very
slope.
quickly,
Yeah. And you see on like this low level, you see how the CCR is following right along with what we're doing? That's because, thermally it's connected to it, right? But at some point here, as we go higher up, and then the gradient will get larger. Yeah?
I think that's the only thing other than the almost set point temperature enter.
Yeah.
Power enter. That's it.
Yeah.
Yeah, that's all we
Pretty
need.
much.
For now, yeah.
But I think the thermometer increased so fast, that's not really good. The temperature is very, very
Well,
fast, very short time.
if it's too fast, then that's what you use the ramping for.
You set heater power for medium.
Medium,
From now
yeah.
go, it's not gonna go.
Well, medium, it'll fall off, right? So like you see how the high is going kind of straight up, right?
Yeah.
So what'll happen is medium will look more like this black line, where it'll start to go up, but then it'll really start to fade fast, and it won't do anything. Yeah. So what you would want to do then is set point ramping.
Yeah.
So you would say, I want 1 Kelvin per minute or
Right.
something, right?
Right.
And then
More
it's
stable.
just gonna staircase up
Yeah,
to
more
your
stable.
set point, yeah.
What chance are going faster?
Unfortunately, the temperature of the material will shrink or
No.
Heat up too
No,
fast?
no.
I don't know.
No.
That would be your application. But yeah, set point ramping then is what you would use. I'll show you when we get to here.
Oh, you can do it in steps.
Yeah.
Yeah,
Yeah, that's the easiest way. You
Yeah,
go
yeah.
from 20 to 40, then from 40 to 60,
Yeah,
then from 60 to 80, from 80 to 5.
No,
So it's
yeah.
excellent. So, and then you can do it with any speed you want, because you can stay
Yeah.
long enough.
Yeah.
Because it's better not to mess up with the controller, because if something goes wrong, you have to study the whole book and then understand what did you do. Not you, somebody else did wrong.
Paul, do we have other way to ram it up? Like I just choose the set point and I choose the time for the system reach to that set point. Could we do that?
so
For
set
example-
a set point.
Right now we have 100, right? Maybe I would like to choose 200,
Yeah.
and I want to the system move to 200 in 1 hour. Could we do that? So in
Yeah,
that case, we can
well, you would
we
have
can
to
lead the
figure
system.
out your ramp, like how fast you want it to ramp,
Oh,
right?
He's telling like, can we control the time here and then set it our system to 1 hour and then leave it after 1 hour it will go. So how we are
Oh,
controlling?
no, you need a computer.
Yeah.
Instead of, if he wants for longer time, I think instead of going to high, we can change it to low, and then heat will slowly ramp up, right? If we,
No, because low
Not
won't,
low,
it
medium.
doesn't have enough power, it's not gonna do anything.
okay, medium would be okay, right?
Or we can reduce the I.
Or we can change the PI maybe.
No.
125 will take half an hour, you mentioned, right?
Well, so you wanna, say again what you wanna
If
do?
you want to do it slowly.
Yeah.
Yeah, so that's set point ramp.
Yeah.
Yeah.
So then in
That's
that
the only
case-
way you can do, to control from A to B, that's set point ramp.
And you are going to show that?
Because right now, we're just saying, from A to B, get there as fast as possible.
okay.
That's what we're doing.
That a system do.
Yeah, and it's just, you know, we just told it go from 20 to 100 as quick as you can. If you want that to be timed, then you have to do set point ramping. Okay, so here we overshot like 3 Kelvin, almost 4. So almost 4 Kelvin overshoot.
But it's not too bad.
And so that just depends on you again, like, oh, yeah, if you're saying, oh, that's not so bad. So again, it just depends on your application, if that's okay. So here I could lower the p-value, right? So that it just didn't go as high. And so I could just start like what I would do, I would lower this by 5, so I go 70, 65, and see the response. Once you find the number that's good, that's it, you're done. It's gonna be the same from this point on.
I have another question. When, let's say I have a sample, I arrange to probe, I did measurements at low temperature, now I have to go to higher temperature. Should I leave the probe?
So it depends, okay? So there's some probe tips that have. So there's 2 types of probes. This is called a CVT probe, right? And you see that it has a little spring. Yeah? And that's to go from, leave the probe down and go through a large temperature. Yeah. So you would want to use these probes. So like right now I have 1 of these in there, and then I have 4 of the just no spring ones. Yeah. And even these ones can do a temperature range, just not as much as this one, right? Because it really depends on the material, the pad, thickness. If you use tungsten or beryllium, your material, because like tungsten, if you were expanding, it would just dig right into your sample really bad. Where the copper's going to ride on top, but it might move more.
So
Right?
which
You have 4 of these and 1 of these. 2 beryllium and 2 tungsten. The beryllium is soft. The tungsten is hard. Yeah. And this is a training kit they send with me, because we might break some of these. The handling. But you can just order these kind, the tip size and the material, which type of material.
I think we know exactly where he's seeing all the data out.
Which arm has the spring in it?
Yeah.
Is that what you're saying?
Like,
Yeah, this arm right here has the spring mount, the CVT program.
How can you see it?
You can look, I can look, just look down and you can see the little spring mounted on the head.
Yeah, I can see.
Yeah, so one has that metal spring on it, the other ones don't. Yeah. And like I said, the other, see, because that's what people are doing before they build the CVT probe, is they would just use the regular probe, and yeah, you would have to find out how much temperature range you could go before you had to move your probe. Yeah. And David Dalton, he's the scientist. I gave him
Yeah.
their email.
Yeah.
He's the guy that you would talk to about. Here's the material I'm using, blah, you know,
What is the
this,
better
well, how do you,
probe?
yeah.
Okay, yeah.
And then he could help you maybe of which probe, like the material, the size, like stuff like that. Yeah. Okay, so even though we overshot 4 Kelvin, it only went 2 iterations of the set point, and it's flattened out to.
Yeah, that's pretty good. Yeah.
So if you didn't like the 4 Kelvin, then we would drop the P value. So, okay. So now if I wanted set point ramping, so I go into input, sample. Oh, output, and output 1 is the sample stage, and here's the set point ramping. So I would turn that on, and then next down, now it tells me how many Kelvin per minute do I want to go, right? So that's, yeah, and whatever you put in there.
All right.
Put in.
And it's all in the manual, right?
This part would be in the manual for the 360.
Okay.
Yeah.
So we'll go over the
Yeah.
Okay. So 250 now. And we can leave everything the way it is.
Yeah, I'll be for simply.
Yeah, it's still high. Yeah, from now on, it's just high all the way through. And we'll see. So you'll see the heater come on here, man. But even that only took, yeah, about 5 minutes to settle under the 50 millikelvin. So it's still pretty fast.
And how can we see again all ABCG?
You just push the button.
Oh, okay.
Yeah, so that's what the radiation shield is doing, the arm, and the CCR. And now you see that now the CCR is able to, yeah, that gradient is just going to stay down there now. In the beginning, it follows really closely. See the cold head? Because they're both like at 8 Kelvin. Now we start heating this up, some of that heat's going to go to here as we go up.
So after we finish working with the tool, we have to set the temperature to 0 or something. Then it will cool down.
No, you could just say all off. You could, yeah, you could put a set point to 0.
Okay.
You could say all off. That would turn the heater off.
Okay.
And once the heater's off, that's on 100%, so it'll just start cooling.
I see.
Yeah. Typically, I tell everybody to set a set point of 0.
Yeah, I agree.
Because one thing is if there's a set point in there, I can turn this on with one button. If there's no set point, that forces the next person to be able to turn this on. You got to put in a set point.
Yeah.
So it makes it so that somebody can't just come up and accidentally turn it on.
So better put it to 0.
Yeah, so that's what I put it back to 0 is always, because again, it forces the next person in line. They have to do 3 steps to be able to turn it on.
What are those?
Set point. So they're going to say A, set point, put in the number and enter.
Okay, okay.
Yeah. If there's a set point already there, all they have to do is say on, you know. And if there's like, say it's, you have the cover off and there's no vacuum. So you don't want to run the heaters with no vacuum, right?
Yeah.
Because they'll burn up, they can
Yeah.
burn up.
So when we set the set point to 0 before going, then we don't have to click on all out, right?
All this is telling you that this control is active.
Yeah, so we
The
don't have
loop is
to,
active.
so we don't have to turn it off,
It's
right?
very important.
We don't
If
have
you
to.
put this to 0, yeah, it's again, this is just telling you that the channel's active.
Okay.
that the loop is active, right? That's why, so again, if I put, I have to turn the heater up, so I'd have to say like set point 0 or, yeah.
So when we turn the the set point 0 and really, I mean, all the system is running and keep the temperature as low as possible to 0K.
Yeah, that's gonna stay cold. And as long as the compressor's on, that's on 100% always. Yeah. And we're just trying to find enough heating power to go against the 100% for stability. So you see, it's not quite as fast as it was. It's slowing down. So just because, like,
Difference is a lot.
well, we're heating up more mass. That's kind of reacting against it. So as you go up, it takes a little longer. Down is easy. Say from like base to 100K, it's pretty fast. Once you start going past 100K, then it slows down. You see, our slope is a little bit slopier than this one.
So why did you mention 500 Kelvin your max?
You'd have to look in the manual. That just has to do with the resistive of the sensor, some information about the sensor. Like if you had an issue with this and you called service, they're going to ask you a whole bunch of stuff like what those numbers and there's a bunch of secret buttons and stuff that you can push for diagnostics that they're going to like troubleshoot you with you to find out if it's this or if it's that.
Okay.
So like if the heater fails, so like right now we have a heater on, right? And say this heater failed, the controller will shut down and it will come up with a message saying that the heater failed, and it will tell you if it failed because it's either shorted or open. So, so the controller is going to kind of tell you that it thinks that heater is shorted or opened, right? So what you can do then is, and if you call the service, this is what they're going to tell you. So on the back of the controller, these are the heater cables. These banana plugs, right? So these banana plugs, you would just pull this out and put a voltmeter over it. It's a 25 ohm resistive heater, right? Yeah, so you just read this, and if it says 25, then it could be the controller. If it says shorted or 0, then the heater inside here is something wrong with it. Same with the sensor. They will tell you to push a bunch of buttons and it will tell them if the sensor is bad in here. Because like sometimes the sensor, it's in a little package, and if you heat the package up too much, it can bond and stuff like that. So sometimes it can be the heater or the sensor inside here, and then you'll have to, I'll have to come out and replace them. It doesn't happen too often, but it still happens. They're really, I've been doing this 14 years, and I have maybe 3 service calls a year. And it's usually on older stuff, that's already been there for a while or something. They worked really well, and it seems, also, like any Lakeshore stuff is a 3-year warranty. So if a heater or sensor went out, that's warranty for me, work. So they usually don't care. If you want to practice with the probing and how it moves and land, you can do that. Focus the microscope.
I have question about fiber.
Yeah.
Okay, so we cannot see it.
It's right here.
It's right here.
Yeah,
Oh,
that's
this is
the
fiber,
glass
yeah.
fiber right there.
Oh, all right. Okay,
Yeah.
that's very good. Okay, so we can see. Can I play a little bit?
Yeah, you can do whatever you want.
No, this is zoom and focus is right
The
here.
zoom, and this is the focus right here. This
This is
one
the
right
focus,
here.
yeah.
Yep. And then the zoom is out.
Oh, yeah, well, now I can see it, yeah.
Yeah, it's glass, so it's hard to.
No, no, it's
Yeah,
okay.
you can
No,
focus kind of.
yeah,
But Paul, can't we see the optical fiber very clearly through the microscope?
That's as clear as you're gonna see it, I guess.
Which is
Because it's
reflected
glass,
here,
so
yeah.
you're
Yeah,
seeing
this is-
through it.
Yeah,
like-
this is just the cover of like the.
No, this is the
beneath.
cover right here.
I mean, like if you remember, like the optical fiber is through one.
Yeah, it goes
plastic,
through
right?
and it sticks out a little bit.
Yeah, yeah.
That's what this is.
Yeah, yeah.
So
So,
which
but
one
we
is
can
that
see
with
the
the
fiber
optical,
here,
right?
right? We
No,
see the.
this is the fiber.
Oh, okay.
That is the little thing sticking out. The what you're talking about is that. This is that plastic part, the
Oh,
holder. This
okay.
is the holder right here, and you know we went through the hole,
Yes.
Yeah.
right, and the glass is sticking out like this,
Okay.
and we're looking just at this little part right there.
I see.
That's
Oh,
the
okay,
yeah.
that's
So
that.
that's the glass right there. This part.
Okay.
So you see, this is rotate, so it doesn't really go X, Y. But, yeah. So yeah, this is going to go kind of side to side, and then you have to rotate it this way to get
And
up
how
and
you
down.
take that to the gas?
It's better like maybe here. So
Oh, alright.
like what I do is I loosen this enough where it holds it,
Okay, and then.
but you can still move it. You know, so if I move it, it stays there. And I move it back, it stays there like that. You know.
Yeah, and then you live and you see.
This is not up here. You just rotate it.
Yeah,
Yeah,
it's
it's
kind of they're actually looking at because Janus,
Yeah.
their optic system is actually X and Y,
Yeah.
and I think they're looking at, you know, again we're gonna use some of Jan's stuff, they're gonna use some of our stuff.
Yeah.
Talking about using their microscope and stuff.
Yeah, it's a
Because with RF, when you're doing RF, you gotta have that XY movement to get to your pad light,
Right.
and so it works better that way if it's a really XY.
So right now is 550 is tungsten.
No, this is tungsten. That's beryllium, tungsten, and this is the CVT one, which I think is tungsten as well. I just know that because the reflectivity of it. The copper is real dull looking, and the tungsten is real.
What
That's the fiber optic.
okay.
So that's just glass, the glass rod.
We have three tungsten.
Two tungsten, two beryllium. Well, this is a tungsten because it's the CVT. So I, like in the kit, I have two copper and two tungsten. Yeah. So those are the tungsten, those are the copper, and this is that CVT. So you see the CVT one, and compared to this one. So when I land this one, so this is just a regular probe. And you see how it pushes forward like?
Yeah.
Yeah? So this one is the spring-loaded one. And you see it moves this way because it's on a spring, so as I come down, the probe moves like this, right? The other one, when I come down this way, it spreads the tip forward. So that's kind of the difference in the landing of the probe.
So with the sample so hot, we could use 10 tungsten, right? With the sample,
That depends on your which ones you use. Kind of depends on your application. I think, like, you know, because the pad, the thickness, the material, that will all come into play. Because like tungsten is really hard and sharp, so it'll go through oxide and gold, and you know, and where the beryllium rides on the top of the surface, and will just, you know, so. And there's other flavors. There's plenty of, you know, that you can use. It just again, maybe your application. You know, like you can talk to David about that.
So,
You know, like here's my application. What probes you think would be the best for me to
could
use?
could you explain a little bit about this one? This is tungsten, this copper.
Yeah, tungsten, copper, and this is tungsten as well.
So we have 3 tungsten.
Yeah, one CBT and one just regular.
What is CBT?
That's the one with the spring load on it. This one has a spring load. These don't. These are just normal.
What is spring load?
That's. I showed you. Oh. Yeah. So that's the little. See, there's a little spring on the. See the little probe tip? Seeing that there's a spring on it. So this has a spring, the other ones they don't have. It's just mounted to the ceramic body.
Can you show
So
me?
this one no spring, right?
This is
There is a
spring
here.
loaded.
There
Yeah.
is a spring here.
That is the spring.
Oh,
This
okay.
whole silver thing.
Oh, this one, this on
Yeah,
this.
yeah.
Okay, okay.
Yeah, and then you see the probe is welded to that spring.
Okay, okay.
Yeah.
Other one does not have this one.
Now it's mounted to the ceramic body instead.
Okay, okay.
When we open it later, you'll see. You can see what the difference.
Yeah, I just have a moment in this thing. Take a look, you tell me up.
So the function of the spring here is just make sure that the tip is quite slightly.
Well, it's so that you can go through a temperature range without picking the probe up, is the idea. Yeah. So the spring is going to take the expansion of your sample. And then you don't have to pick. Because normally, like with these probes, you're supposed to go to your set point, land your probe, it'll acclimate, you do your testing, then you pick your probe up and you go to the next temperature.
Oh,
That's like kind of normal, but everybody wants to leave a probe down, right? So, you know, they have been using these ones for to try to do that a little bit, because it'll work for a smaller temperature range.
Yeah.
But this one, then they developed this one, and like David wrote a paper about it. You could ask him about that, and it's just basically again so that you can leave your probe landed and go through a larger temperature range without having to pick it up. Yeah. And depending on your application, the material, the pad size, thickness, which probe you use, how much that window might be. Yeah.
Let's see.
So we made it to 250. You know, it looks like we overshot like a 1 1/4. So a little better response that time. About 2.5 colors. And then, but we'll see how it comes to the second. So this would be a nice point when you go up in higher temperatures if you had some control of your cooling power. Because then we could lower our cooling power and then this would happen faster.
So you can turn it off, right?
Yeah, you could, but then you got to turn it back on at some point, yeah. That's why like a flow-through system, you have a lot of control. Because you can control your cooling power through the whole process. Where this is just on 100%, and we're trying to find the heat power that can deal with it.
In turning it off, it's not good for compressor.
You know, I don't know.
But
I haven't heard of anybody trying that.
Well, my students did.
Did they?
He didn't tell me, so I didn't know about it, but it's still working.
I mean, would it matter? Because I mean, you're gonna turn it off when you're done. It doesn't, there's nowhere in the manual that it says it has to be back to room temperature before you can turn it back on. So, yeah, I would say you could do it. Yeah, and then you just have to find out when to turn it back on. Yeah, so that you didn't, because otherwise you might absorb so much heat in the whole thing by the time you turn it on. Because basically what we're doing is we're cooling down. Inside there is a huge, it's real thick piece of metal mass. It's like this tall, looks like a bullet. We're really cooling all of that down to be able to keep the stability and temperature that we want at the sample state. So if we warm all this up, it's gonna warm the, yeah, I don't know that's something that you.
How long do we need to regenerate the travel pump?
How long what?
Yeah, do we need to regenerate the travel pump? The travel pump we need to regenerate the brain.
Oh, you mean like recharge it or something, or what?
Warming it up and pump it. Oh, we don't need it all the time.
No, it's 724 forever. Yeah, really, there's no. These are designed to run 724. That's what semiconductor. This stuff is all used in semiconductor. They don't shut down. It's only maintenance, you know. If you were to leave it running 724, then you would have to do the yearly maintenance.
No, we're not going to do it.
Normally, no one that uses our systems runs it 724, and so it's like 3 to 5 years. So your yearly maintenance is really like 3 to 5 because you don't use it enough to do it yearly. So like there's a seal in here that's supposed to be changed every year, but because you don't really use it 724, it should last about 3 to 5 years. That's what we figured, right? And the way you'll know that is like, so remember I told you every time you vacuum down, you should see these same numbers, right? So like right now it's 1.2 minus 6. And over time that's going to slide up as that little seal. There's a Teflon seal in the front of this that's going to wear out, and then your vacuum will start to slide up over time. So say in a year you look at this and it says 3 minus 6. You know, still okay, right? But at some point you might have to change that seal. Yeah. For the system, there is no cleaning or maintenance. Like you don't want to like clean the inside or anything.
Just keep it clean. Don't mess with it.
Yeah, there's nothing. Yeah, there's no maintenance inside. The manual gives a maintenance chart in the back, but so, yeah, keep this space area clean.
Okay, number one.
Surface, yeah, if you ever have any condensation, 3 months. Yeah, like here, it says clean the inside of the vacuum chamber. You don't want to do that.
No, we don't.
There's no reason, and you could damage more
Or
trying to
contaminate,
clean
yeah.
it. I don't know. There's, as long as you're using nitrogen and purging, it's clean. Yeah. Well, the clean the sample holder, you may do that because, like, there's different ways, of course, to mount your sample. Silver paste, vacuum grease, all that stuff gets dirt. You know, you might have to clean your stage. So that would be like something that you're gonna do all the time, not necessarily yearly. check the compressor cooling quality, you know, again, the water quality, if it hasn't changed. Lubricate the lid O-ring. Clean the viewport window. And then here's where it talks about charging the compressor. So like here, every 20,000 hours of operation, 10,000 hours. For you, that's probably going to be, again, not every year. It's going to be further down. And you don't need to recharge it as long as it's not failing. You know, this is something like you wouldn't just change it just because it was 10,000 hours either. And then 30,000, like, so the oil missed the absorber inside the compressor. They're saying like 20,000 hours, right? So normally when those things start to go, you'll hear like the motor might start squeaking. See what I know the motor starts kind of making some noise. And maybe the compressor might be a little louder. Like you hear it now, it doesn't make any noise, really, yeah. And so normally those things you would notice, right? And not based on 10,000 or 20,000 hours, it could go a lot longer than that.
Okay, so the plan is to go to room temperature, right?
Yeah, we got to go to 350, make sure, so we're at 250 now, and it's just settling. So you see our settling. It's it looks like the p-value could be a little better. See how we're kind of getting this ripple, you know, where it's not flattening out.
But I think it's alright because it's a very fine temperature.
Yeah, it's only 150
Yeah,
volts.
it's alright.
Okay, so last step 350.
So and then we're going to open it up, right?
Yeah, well, so once we get 350, and then we're gonna set it up to go to room temperature, and but it takes about 2 hours to warm back up. So typically that's lunchtime.
Oh, okay, so we're going to open after lunch, right?
After lunch, yeah. So it's gonna warm back up to room
So should
temperature.
we turn the compressor off?
We will,
When
yeah.
we reach 300?
Yeah, once we reach 350, then we're saying, okay, we're done. Then we're gonna turn the compressor off, and we're gonna set this up to warm up to room temperature. And then it's like
So I
Two-
think
2.5 hours.
maybe instead of 350, we can go to 300, it's going to be faster.
well, I want to make sure that it will
Oh,
do,
alright,
yeah,
okay.
Yeah. So we're just doing the full
Full
range
range,
of the
yeah,
system,
okay.
make sure everything works, yeah.
Paul, I have a question.
Yeah.
We did not turn off the compressor now when we are raising the temperature, right?
Yeah.
But then
we
why
did.
do we need to turn off the compressor later when we want to got the room temperature?
If you, I think I explained to him this morning about room temperature. Okay, so if you just want to do something at room temperature, you won't have any control. It'll just be whatever room temperature is right now.
Okay.
So you have, if you want any kind of control, you have to have the compressor.
Okay, if we are working with the temperature, then we have to have the temperature on.
Yeah.
Because then
Oh,
we keep
oh,
it
yeah.
at
Only
one
like, so
time,
again, so like yesterday, room temperature was like 293 here, right? So you can do stuff at 293 and that's it.
But
You can't control it.
so today we have to check the temperature of the room and then we should set it.
Do what?
Should we go up to 350 to turn off the compressor or?
Okay, so let me explain it. Okay,
No.
no room temperature measurements will be done in this system. Okay, room temperature measurements use something else. That's it. Okay. So this is low temperature setup. It's going to be used for low temperature measurements.
The compressor has to be on all the time.
Okay, so no
When
measurements
it's,
at room
yeah,
temperature. Period.
the compressor only, like again, if you're if you can only do room temperature or what it is, no control. So if it's 293, that's what you're doing.
And it
293.
fluctuates, of course, you have no idea what it is exactly. It fluctuates with temperature in room.
It could some, yeah.
You
probably
open the
not
door,
too-
it's already a couple
Oh,
of
it does.
degrees.
Oh, okay. So, yeah, there'll be some. You just won't have any control over it, and it's gonna move some. I don't know
one
what.
question. Are there any interlock for the
Interlock.
Yeah, for
For-
heater. For example, no, I mean, at high pressure or at atmosphere, the
No.
heater will not turn on.
No interlocks. You're super user.
Well, it's, the common sense.
Yeah.
Or some set of rules. Okay.
Yeah, more of a set of rules. we might not be able to go on common sense alone.
Yeah, you're right. Yeah. Better to-
That's why rules
Yeah,
work.
rules are better.
They're usually written down.
To open it up, so we have to release these screws, right?
After once we pressurize
Yeah,
it.
the
Yeah.
pressure to release these screws and release the whole thing.
Yeah. Yeah. That cover, and then the next cover is the rad shield, and then that will come out too. There's two of them.
Yeah, I can see.
So yeah, so see right in there, that glass piece there, that's the rad shield cover. So this cover, rad shield cover, and now it's, so like here. So here, like here's the rad shield cover right here. And then with both of them out, now you can have access to the inside.
So which is radiation?
This one.
This one.
Yeah. So this is chamber covered, and then underneath that is the radiation shield.
And just again, to have better thermal shield, it may be better to cover the window.
Yeah. So a lot of people do. They'll cover this, right? Because it does like these lights and this light will have an effect. Yeah.
So if we put the system in the clean room, maybe we don't need to cover.
If you what?
I mean, if we put the system in the clean room, maybe we need to cover.
Okay, so you're not ready for the room temperature. Only for room temperature. Because if you accidentally go on the heater, so you're going to break. I think Durga, if you need to do some in room temperature, I think I gave Durga a couple of years back a very good probe station. With probes and microscope and camera and screen.
Yes, you are doing the measurement in heat bath.
Into what? Yeah. I remember his probe station something was wrong and we gave him one from the teaching lab because he got it.
A very big one? Or?
Yeah, it's a pretty big one, yeah. I don't remember how big it is, but it's pretty big.
It is very good one. The one that they are using is very good system. And then I think it's semiconductor and light.
We'll see if we can actually. It's not good to think, to but maybe we can buy another one.
A lot of people use this cap. It's the same size as the coat.
I just want to ask you.
Yeah. So we use that. A lot of people will use that.
Paul, do we also have that thing for labeling? Like yesterday we were doing, right?
The labeling.
Yeah, the label of the table. We were trying to do something like bubble one.
Level.
The bubble label. Label.
Oh, the bubble level.
Yeah.
What about it?
So we have extra one here in case it moves.
Oh, you'll have to buy them.
Oh, we have to buy it?
Yeah, that don't come with, that's like in my food, that's my food.
So maybe you can turn the lights off, right?
Yeah, the button, or you can turn the knob all the way down, whichever.